So we said one of the ways that we're going to need to deal with the moment of inertia is if shape doesn't matter. And so what does that really mean? Well, fundamentally what it means is that your object can be treated as if it were a point particle. So there's a way to calculate the moment of inertia for a point mass that's given by the equation sitting here in the middle of the screen. So the moment of inertia I is equal to the mass of your object times r perpendicular squared. So what is r perpendicular? Well, part of this, again, the moment of inertia cares about the axis of rotation. So in this case, let's assume that we've got something like the moon going around in orbit. It's orbiting effectively. Let's assume its orbit's circular. So it's orbiting around an axis that runs through the middle of its orbit. And so what this r perpendicular is it's the perpendicular distance from the mass to the axis of rotation. So in this case, it would be what's the radius of the moon's orbit. Now, using this equation, we can think about what the units of moment of inertia are supposed to be. And so obviously, if I'm taking a mass and multiplying it by a distance squared, that means that moment of inertia has to have units of kilogram meters squared. And so whenever we calculate out the moment of inertia, regardless of whether we're doing it for a point particle or any other type of object, the moment of inertia is going to have units of kilogram meters squared. So let's change this a little bit. So instead of having a situation like the one pictured here, where we have the moon basically going in a circular orbit around an axis, what if we have, let's say, a ball that we've tied to the end of a string? And so again, here we have our conical pendulum as it's swinging around, undergoing centripetal motion, swinging around in uniform circular motion. But notice here that, again, the length of the string is not the perpendicular distance r that we want. So r perp here is the radius of the circle that it's going around, but that's not the length of the string. So again, we always want r perpendicular to be the perpendicular distance to the axis of rotation. I need to make sure that the length I'm plugging in is the length I want. Well, so what if instead of having a single object going around like this, what if I let's say had a couple masses sitting at the end, instead of these being strings, let's make these sort of very tiny massless rods so that we can give this some rigid structure. And now I want this structure to sort of, again, spin around this axis through its center. So if there are multiple particles that I need to calculate the moment of inertia, well, the nice thing is that it's basically just sum up the individual moments of inertia. So calculate the moment of inertia of particle 1, calculate the moment of inertia of particle 2, add those two moments of inertia together. That's going to give you the moment of inertia of your system. So the nice thing about the moment of inertia is as you create increasingly complicated systems, the moment of inertia of your system is simply the sum of the moment of inertias of all the pieces that you've used to build the system.